He took the time to show me straight to the door.
Okay, so now that we've learned a little bit about the chain rule, we're going to kind of build off of our knowledge, what we just learned, and we're going to apply it to something a little bit different. So this is going to be called the chain rule for paths. Okay, so chain rule for paths. So first of all, what is a path? We're going to define a path as some kind of c of t, and that is an arrow, so this is a vector valued thing or function. So this is going to be x of t, comma y of t, and a z of t. Okay, so this is basically this is kind of like a path is what you can think of it as like path is like a moving point. Okay, moving point, not as like vectors attached to it, but more or less just a point moving along, right? So and then this the derivative of that would then be x prime of t, comma y prime of t, and z prime of t. So each of these components, the x, y, and z components respectively, depend on the variable t. Okay, so this is our t is our parameter variable. Remember we learned about parameters. So anyways, so we've learned about these before, and we know that the tangent vector, this thing here, right? So tangent vectors, another important thing to note. So a refresher, tangent vector points in the direction of motion, right? So in which way is this point moving? Okay? All right, so now knowing that, then we can see what is a composite function. So let's see, composite function, and here I'm just building up to the chain rule for paths, right? So these are all relevant concepts. So a composite function is when you have a multivariable function. So we have a multivariable function that is dependent on a path. And by path, I mean something like above, right? So this one here, this is a path. Okay, this describes a path. Okay, so an example of a composite function would be like a capital T of x, y, z, where each of these x, y's, and z's depend on our c of t, where these can be drawn. So these will be drawn from or taken from our c of t. Okay, so what we get is actually something like t of c of t. So here we see one function making up the other one, or kind of like determining the other function, right? So t here is dependent on our c of t. So we have an outer function and an inner function, so therefore it's a composite one, right? So another way to write this is that we have a t of x of t, a y of t, and a z of t, right? So something like that. So an example of this, like what's an application of it, would be like T standing for temperature, okay? So an example would be temperature depending on your positioning, or depending on where you are or something, depending on location, we'll say, okay? So that would just be an example, like if you were standing in a room and there was an air conditioner or a fan on one side, let's say, then you would say, okay, well, it should be cooler right by the fan, right, if it's a hot day, and et cetera, et cetera. So there would be the temperature depends on your location in the room, or your position here, okay? All right, so now that we have established that, we have our t of c of t is equal to t of x of t, y of t, and z of t, okay? So we have that outer function and the inner function, which is the path. Okay, so now what we're going to do, because this is calculus and we love to differentiate, is we're going to differentiate, basically. We'll differentiate with respect to t, okay? And notice how here we actually only have normal d's, right? Not the curly ones that stand for partial, because our entire function here, everything that you see above depends only on t. T is our only parameter, right? X, y, and z are just kind of like middlemen, right? Those are the... So yes, so t is our only parameter variable, because x, y, and z are kind of like I was saying, the middlemen, I guess. We have to go through those to get to our lowercase t, right? So t is our parameter variable. That's the only one there that anything really depends on. And so then we would have, so if we're differentiating both sides, we would have ddt of capital T of c of t. Sorry, there we go. 3 sets of parentheses. And then on the right side, what we would get is actually, so here we're going to implement the chain rule, right? Because we have this outer function to differentiate plus this inner one that it depends on, that is composed inside of it. So what we're going to have is we're going to differentiate the outer function, keep the inner function the same, right? And then we're going to differentiate that inner function. So then we have dt of c of t, okay? All right, so this one, let's look at this. So here, remember t, our outer function, that's actually a t of 3 different components, right? This is a multivariable function, this outer one here. So since this is a multivariable function, the derivative of a multivariable function is something that we just learned is the gradient. Okay, so whenever you see something like that, a multivariable function, and we're taking the derivative, that means we're going to take the gradient of it. So what we're going to get is a vector, right? A vector out of that. And then look at this quantity here. This one, this is like the derivative of our path, right? And this is a single variable, so we don't really have to worry about that too much. That's just our normal c prime of t, okay? So anyway, so let's deal with this, and let's see where we go from here. So ddt of capital T and c of t is going to be equal to, so this is the gradient, right, like I was saying. So this will be the gradient of t with c of t inside, okay? And then this will be dotted with our c prime of t. And this is not only multiplied anymore, because now we have, this is a vector quantity, and this is also a vector quantity. So since we have 2 vector quantities being multiplied, we have to take the dot product. So this is a dot product, okay? All right, so in a more, I guess, detailed sense, what would we actually see? This would be, if we're taking the gradient, that means the partial derivatives for each component, right? So we're going to take the partial of capital T with respect to the x component first, so this first spot, comma, the partial derivative of t with respect to y, whatever's in the y component, okay? And then the partial derivative of t with respect to z. Okay, so that's our first vector, and then we're going to dot it with our c prime of t, which is basically just x prime of t, y prime of t, and z prime of t. Okay, so that's our, move the whole screen there. So that's our second vector there, all right? And then if we were to do the dot product, what we would get is the partial of t with respect to x times x prime of t plus partial of t with respect to y times y prime of t plus the partial of t with respect to z times z prime of t. Okay? And another way to write that, I'll continue this on the next slide. Alright, so if we continue that, then we get the partial of t with respect to x, and then x prime of t is the same thing as saying dx dt, and these are normal d's, right? Because this, our function x, depends only on t. That's a single variable thing, so we have the normal d's. And then similarly, we have partial t, partial y, dy dt, plus partial t, partial z, dz dt. Okay? So that's basically it. And then, so this is for in 3 variables. This is a 3 variable case. Again, this is the, not the gradient, sorry. Hold on there. This is the derivative with respect to t of c of t there. Sorry, I kind of squished that in there. But that's what we have. This is just another way to write it. And on the last slide, on the previous slide, where everything leading up to this step were also different ways to write the derivative. Okay? And so like I was saying, this is in 3 variables. And if you were just working in 2 variables, all of the z stuff would be 0. So then this would just not be existent. And you just get that. Okay? Alright, so now let's do an example of this chain rule for paths. So what we're going to do is calculate the derivative with respect to t of f of c of t, okay, at t is equal to pi over 2, where we have that the given function, the outer function, is f of x, y, z, which is equal to x, y plus z squared. And our c of t, our path, is equal to a cosine t, a sine t, and a t. Okay? So this is what we're given. This is our outer function, depending on just x, y, z. But then we also have that the path that is composed within our f, this is given by cosine t, sine t, and t. So we can kind of label these x of t. This is our y of t, and this is our z of t. Okay? All right. So how are we going to compute the derivative of this guy? So we have to kind of compose it within one. Stick the c of t, the path, inside our f function, our outer function, right? So ddt of f of c of t, 1, 2, 3 parentheses. We're going to use the chain rule, right? So the chain rule would be taking the derivative of the outer, and the outer happens to be a multivariable function, right? I'll label that multivariable, and this is a single variable one over here, right? So multivariable, when we derive those, we get we have to take the gradient, so it'll be the gradient of f, and then we'll still have c of t in there, right? With c of t plugged in, and then we're going to dot that or multiply it with the c prime of t, so the derivative of the inside of the inner function there. Okay, so what we're going to do, let's just find this part first, and then we'll find this part, and then we'll dot them together. Okay, so the gradient of f with c of t plugged in is going to be, so let's see, what do we get? So we have our df, okay, so what we're going to do is take the partial with respect to x for the first component, and then the partial with respect to y for the second component, and partial of f with respect to z for the third component there. That's how we compute the gradient, right? And so this is going to equal, looking at our original function here, if we take the derivative with respect to x, the z's go away, and we just get the coefficient of x, which would be y. And then for the partial with respect to y, we would do the same thing, the z would go away, and the x would come out. Okay, and finally, for the z component, we would just get a 2z, right? So if we have something like that, when we plug in that c of t, what we would get is, for y, we would plug in sine t, okay? Because now, okay, so let me go back a little bit. I'm going to backtrack a tiny bit here. So I'll just rewrite these equations from the path, okay? I know there's a lot of stuff going on. So x of t from our path is equal to cosine t. Our y of t is equal to sine t. And our z of t is equal to t. So now what I'm going to do, now that I computed the gradient of our outer function with respect to its normal variables, x, y, and z, right? Now I'm just going to replace each one of these with what it means as a parameter, as our in terms of our parameter t, okay? So I'm going to plug in a sine t here for the y, a cosine t in for the x, and a t in for the z spot. And I'll do so on the next slide. So we have the gradient of f of our c of t is equal to, and y, we had y for the first one, so that would be a sine t, and x for the second one, so that's cosine t, and a 2z, so that will now be 2t. Okay? So now we have that. That was our first part of our derivative, right? A part of the chain rule. And the second part was simply c prime of t. So that one's just going to be x prime of t, y prime of t, and z prime of t. All right? So originally what we had, so here's a little refresher. So c of t, our original path was equal to cosine t, sine t, and a t. All right? So if we take the derivative of each of those, we get, for the first one, we'll get a negative sine t. For the second, we'll get a positive cosine t. And for the last one, we just get a positive 1, right? Okay, so now all we have to do is, sorry, I always write that. So ddt of f of c of t. See, I have 3 parentheses going on there. Okay, so that is going to be equal to our gradient of f of c of t in it. Okay, so that's this first thing up here. and then that'll be dotted with c prime of t. Okay, so we're just going to plug those in. So we have sine t, comma cosine t, comma 2t, being dotted with negative sine t, cosine t, and a 1. So if we take the dot product, we're going to get negative sine squared t plus a positive cosine squared t plus a 2t. Okay, so this is what the derivative is, and our last step is going to be plugging in, evaluating it at t equals pi over 2. Okay, and we'll continue this on the next slide. So we have d dt of f of c of t, 1, 2, 3, evaluated at t equals pi over 2 is going to equal negative sine squared at pi over 2 plus a positive cosine squared at pi over 2 plus a 2 times pi over 2. Okay, so let's find out what that is. So we have a sine at pi over 2 is a 1. So negative 1 squared, or negative, there we go, 1 squared, plus, and then cosine at pi over 2 is 0, so we have a 0 squared, and then plus a pi. Okay, so this is just going to be negative 1 plus pi, also known as pi minus 1. Okay, so that's going to be the answer for that problem, where we use the chain rule for paths.